I don't profess to be a particular expert in any of this. I don't think I know any more than anybody else in this room. It's just, I hope that I will be able to put this over in a way that most people can understand and move forward. So the objectives really, first of all, I just want to provide an overview of the terms relating to the flight envelope so that people understand generally what we're talking about. I want to give a whole list of reasons why the flight envelope is there and the limits that it imposes, and explain why exceeding those limits is a bad idea. It's very difficult to understand these limits in theoretical terms, so I'd like to try and also relate them back to what you actually perceive in practice. What I'm not going to try and do is give you a degree in aeronautical engineering. So this is a brief overview, and it's just trying to explain some aspects of the theory of flight, rather than trying to provide a degree level course. So many of the references are to CS22 standards or JAR 22. And if you need further information, you need to read them for yourselves. None of this is really required for bronze or solo sort of standard pilots, but all glider pilots should really have an appreciation of what the flight envelope is. And if you're doing aerobatics, you should really understand these limits because you will be getting much closer to them. I hope you won't be exceeding them. So it might be an interesting exercise for you to go and have a look at the flight envelope for your own glider and find out what its limits are and the levels to which you can fly without putting yourself in danger. So I'm going to try and give you some of the terminology associated with the flight envelope, and allow people to understand the concepts involved so that, sorry, my computer suddenly stopped working, so that you can understand what a flight envelope is and go beyond this presentation and do your own research into the flight envelope. Now, unfortunately, when you turn to most chapters in books about flight envelopes, they present you with a diagram like that. And an awful lot of people say, I have no idea what any of that means. I'm going to give up at this point, skip this chapter and move on to something else. But although it looks very complicated, most of it is a series of simple steps. So what I'm going to try and do is to explain what all these various bits and pieces are. This laser pointer. I hope everybody can see that laser pointer, because every now and again I'm going to be using that to point out things on this graph. I'll just move it out of the way to begin with. Right, we call it a flight envelope because you can fly inside it, but you can't fly outside of it. And it is vaguely envelope shaped when you draw it on a graph. So the flight envelope looks sort of like that. It's plotted on a graph with two axes. The horizontal axis is easy to understand, that's in knots, nautical miles an hour. The vertical axis is the load factor, which goes from 0 to 7 positive in this case, and 0 to 5 negative. The load factor is a ratio of the lift to the glider's weight. I'll explain that on the next slide in a little bit more detail, but in most cases it's analogous to G, the G loading. There are a few exceptions, but some people think of it in terms of G, but the correct term is load factor. When we're talking about these flight envelopes, there is no, we're describing a flight envelope for one specific configuration of the aircraft. So this will be with ailerons in neutral, with the rudder in the center, with the elevator in neutral. We're not allowing for, you know, any changes. If you put the wheel down or if you change the flap setting, you would get a different shaped flight envelope. So it's important to remember that every time we draw one of these diagrams, it's for a very specific configuration of the aircraft. So what is the load factor, that vertical scale? It's the ratio of the lift of the glider to its weight. And how can we affect that load factor? Obviously, if you change the angle of attack using the elevator, or if you fly through a gust, you're changing the lift. So that will change the ratio of lift to weight. If you change the weight by venting water ballast or whatever, you're changing the weight. So that will change the load factor. Acceleration is a common way of changing the load factor. We refer to the forces that we feel during acceleration as G, normally experiencing 1G. In steep turns, you can easily feel up to 2G, possibly more. And the winch launch is a very significant phase of flight. When the downward pull of the cable and the push on the tail, horizontal stabilizer, will dramatically change the load on the aircraft. So there are essentially three limits, three sections to this graph. There are limits which are aerodynamic. There are limits which are standards, CS22 or JAR22, and there are limits which are structural. And if you exceed those limits, something breaks. I've already said this, but throughout the presentation, everything that you see relates to one specific configuration. So if you change the ailerons, change the brakes, change the wheel, then you fly into a slightly different flight envelope, which would be similar. It says down here, it will be similar, but the curves and the actual positions of the numbers will be slightly different. So first of all, we'll look at the aerodynamic limits. And the aerodynamic limits are these two curved lines here and here. This is positive flight, positive G loads, and this is negative flight or inverted flight. Most gliders are much less efficient inverted than they are in normal positive flight. Those curves look something like that. This isn't for any specific aircraft or glider. These are just curves on a graph. So don't try and relate them back to a K-13 or anything specific. Essentially, the wing can generate a certain amount of lift. So if you were flying, let's say at 40 knots, then you can generate a certain amount of lift and you can support the aircraft's weight, a load factor of 1. So this aircraft flying at 40 knots can support a load factor of 1. If it was flying slightly faster at 60 knots, then it could support a load factor of 2. This is theoretically what the wing can do. This is not what it must do at every opportunity. So it's perfectly reasonable to fly your aircraft faster, but at a lower angle of attack. So you could be flying at 60 knots and have a lower angle of attack, only generating a load factor of 1. You're only generating enough lift to support the aircraft's own weight. But you couldn't fly slower and expect to generate a load factor of 2 or 3. So you can't fly at 40 knots and generate a load factor of 2. generally speaking, flight into the right of this curve is possible. Flight to the left of the curve is not possible. In other words, this is known as the stall line. The wing will stall if you try to make it work harder than that. There is a dotted line. This dotted line is 25% higher, and the values of this dotted line are 25% higher than the solid line, and essentially the wing can momentarily produce more lift. So if it's hit by a gust, or if you make a rapid change to the angle of attack of the aircraft, the wing will produce a bit more lift, but then it will stall. The airflow will break away from the top surface, a stall will occur. So the dotted line is achievable for a short period of time until the wing stalls. So I've just explained that the purple dotted line is a 25% increased load factor. And I've also explained that most aerofoils would work in the positive G sense and the negative G sense, but less effectively in the negative G sense. Let's get rid of that text. So that explains those two curved lines and the purple dotted line. The next limit is VNE. Everybody knows what VNE, velocity never exceed, means. Don't go faster than this. So let's assume that we've got a VNE of, let's say, 128, I think I've chosen here. This is effectively an arbitrary figure. Somebody has designed the aircraft to fly up to a certain speed. And you have been told never to fly it faster than VNE. They've actually designed it to fly up to a speed known as VD, the design speed. And that's, VNE is 90% of VD. So there is a little bit of buffer space in there. They've designed it to be a little bit stronger. And so theoretically, it could fly up to VD. However, at some point, some test pilot has taken a brand new aircraft out of the factory and test flown it up to a speed known as VDF, the design speed which has been demonstrated by fly. And this is 90%, 95% of the design speed. So the test pilot has flown beyond VNE to VDF, but possibly that aircraft has only once ever been tested past VNE.
John, do they only do that for the prototype? With every aircraft coming off?
No, that's only done once for an aircraft.
For a type?
It's not done for every aircraft. So if you exceed VNE and get anywhere near VDF, you're into test pilot territory, and you will not be flying a brand new aircraft straight out of the factory. It's interesting to note that there are only 7 knots between VNE and VDF. So as I've just said, if you exceed VNE, you haven't got to exceed it by very much in this aircraft before you're a test pilot. Now, the position, the speed at which VD, the design speed, occurs is specified in JAR22 or CS22 by these equations. This is totally irrelevant. You don't need to know any of this. But if people say, where does that come from? That's where it comes from. It's to do with the wing loading and the drag. And so you've got a metric and an imperial version of the same calculation. If you want to know more about JAR22, there's a load of information on Wikipedia and you can click any of these links, which will give you further information. There's also, you can also download CS22 from this website. Just search for CS22, you'll find lots of links. Or I can give you this. CS22, whereas on the previous slide, JAR22 explained it in very simple terms very quickly. CS22 explains it in a much more complicated way. It goes through VA, VF, and then on through VB, VT, VW, and finally we get to the same calculations that we saw under JAR22. As I've already said, you don't need to understand any of this. It's just that's where it's defined. Right, moving back to the flight envelope. Beyond the designed maximum, the reason that the design maximum is there is that beyond that, you may potentially lose stability. I'll explain that a little bit better in the next couple of slides. The other thing that may happen if you try and fly too fast is that you get flutter. And again, I'll explain that a little bit more in the next couple of slides. Flutter is much more likely to occur if there's any play in any of the control surfaces or it's outside its design mass limit, so somebody painted it or made a poor repair. So the first thing we're going to look at is the potential for loss of stability. To do that, I need to divert momentarily into the theory of flight and explain why that stability loss occurs. Excuse me. So assume we've got a K-13 flying at a sort of a normal airspeed. We'll define a couple of terms. There's a chord line, which is the line passing through the leading edge and the trailing edge. And that's at a positive angle of attack to the fuselage, but it's also at a positive angle of attack to the relative airflow, the air flowing past the K-13 in flight. And the angle between the relative airflow and the chord line is known as the angle of attack. Just defining terms here. Simplify that diagram a little bit. Now, the lift generated by an aerofoil has a profile. You get a certain amount of lift generated above the aerofoil and a certain amount of lift generated below the aerofoil. And if you add all those contributions together, so there's a little bit of lift here, more lift there, a little bit of lift there, then the center of pressure is the point at which you could imagine all those little contributions of lift are resolved through. So I'll just move that diagram out of the way for a moment, but remember that shape. If we increase the angle of attack, the profile, the lift profile generated by the wing changes. First, the increased angle of attack creates more lift, but the shape changes. It's much more peaked and it's much nearer the front of the wing. So just sort of compare that shape with that shape. What that means is that the center of pressure moves forward. The lift contribution by all of these points of the top surface and all of these points on the bottom surface adds up to the center of pressure moving forward a little bit. And in the inverse way, if we decrease the angle of attack, then again, the profile changes, smooths out a lot compared with what it was originally, and the center of pressure moves backwards. So as you increase the angle of attack, center of pressure moves forwards, decrease the angle of attack, center of pressure moves backwards. So the K-13 in flight we all know that there's a centre of gravity in a K13. When there's nobody in it, it balances pretty much around its wheel. Slight tail weight, but it's pretty well balanced. When you put pilots in it, the nose goes down. So we know that the centre of gravity is ahead of the main wheel, and it tends to be round about here where the the instructor sits in the back seat, so that when the instructor gets out, it doesn't make a huge difference. So the centre of gravity is near the leading edge of the wing. It doesn't matter exactly. There's a centre of pressure, which I referred to on the previous slide, which is where the lift is being generated. So the lift from the wing is pushing up here, the centre of gravity is pulling down there. So there's a tendency for those two forces to twist the fuselage and pitch it nose down. This is counterbalanced by the tail. In this illustration, the tail is producing a small downforce. So there's a fairly strong force here, the lift, and a fairly strong force here, the weight, but the distance between them is very small. There's a small force here, but the distance between that and the centre of gravity is very long. It's a much longer lever. So the tail, the small downforce on the tail is able to stabilise and stop the glider pitching nose down. Now, as we fly faster and faster, I explained in the previous slide that the centre of pressure will move backwards. So let's move the centre of pressure back. This length has increased quite dramatically. It's probably twice what it was previously. So the lever between that force and that force, the lever arm has increased in length. So the tendency for this glider to pitch down is much greater than it was. And the tail may now not be strong enough to overcome that pitch down movement. So if you fly faster and faster and faster, the centre of pressure moves back. This distance increases. This distance between the tail and the centre of gravity doesn't change. So the twisting force to pitch the glider nose down gets greater, but the force to restore it, it has a limit. It can't get any greater. So if you fly faster and faster and faster, the centre of pressure can move back to such a point that the tail is no longer able to stop the glider from pitching further down. In other words, you cannot stop the thing diving into the ground. So that is the potential loss of stability if you exceed VNE, WVD. So back to the diagram.
Can I ask a question, Jonathan?
Yep.
If you fly faster, you would typically trim forwards.
Yes.
So you're decreasing that downforce on the tail in order to fly faster. Those physics would suggest that you need to increase it by pulling back as it is.
What I was describing there is what can happen if you're going beyond the design speed and the centre of pressure is moving further back than the designer had expected it to move. This is not the normal flight regime.
Sure.
Okay, so I'll just mention loss of stability there. Now I'm going to move on to potential for flutter. This is a very complex subject, so I won't try to explain all of it, but effectively the structural stiffness of the fuselage and the wings plays a crucial factor in the possibility that the thing might flutter at a resonant frequency. As I already said, this is much more likely to happen if any of the control surfaces are worn or something's out of balance. The the glider may, or an aircraft may flutter in any of the three axes. People think of flutter as being a control surface, or perhaps the rudder, but the glider can flutter in pitch, in roll, or in yaw, and that will depend on the structural stiffness of the fuselage and the torsional stiffness, whether the tail can twist relative to the fuselage, and the flexibility of the wings. So you can have yawing, rolling, or pitching flutter. The next slide most people will have seen, and it's a glider, but it's a DG glider being deliberately made to flutter at around 81 knots, according to Andreas, who translated the German for me. So hopefully this will burst into life in a moment. And there's no sound. But normally there's sound on that, and he's calling out the various airspeeds. You can see the wings fluttering. I'll move on to the next video. This is a whole series of things fluttering. There's a flag fluttering. That's exactly what your control surfaces might do. There's a tailplane fluttering. There's a. I think I've done that too.
Yeah, I think you did.
But did they actually test it to do that?
These are obviously flight tests. Yeah.
Yeah.
I just found these videos on YouTube. There's nothing. I haven't done anything special. This is the one you just saw.
And that's at 81 knots or something, is it?
They added water ballast to make it do that deliberately.
I don't know what water balancing was.
Everything's going. Everything's going.
Not long for this one. Watch the fins, the vertical. Imagine sitting in a passenger jet and looking out the window of that.
Right in.
You can just see the canard at the front oscillating there. I think the next couple are a couple of model aircraft, but they show the same effects. Oh no. So these are all good reasons not to fly too fast,
Yeah, I can see that.
especially if you're showing off at an air display. Yeah, this is obviously a model, but we'll get David Wild to try this
Yes.
with some of his models.
Do it like that, yeah.
Well, there's just more of the same. I'll move on from that. Right, back to this graph. So flying in this area to the right of VNE, beyond VDF, you are a test pilot, and you may well either run out of elevator and not be able to get the nose back up, or something might flutter and fall off. But it's important for anybody flying at altitude to remember that the airspeed indicator doesn't tell you the truth. So from the PERCOS flight manual, in the utility category, or aerobatic, utility, VNE is 132 between 0 and 10,000 feet. It actually says 9.8, but we'll take that to 10,000 feet. If we go up to 19.7, that's close to 20,000 feet, the VNE is now 112 indicated. This is because the air is thinner at altitude, you know that, because you have to take oxygen. And because the air is thinner, it doesn't impinge on the pitot so much. So the airspeed indicator underreads. And in this case, it underreads by 20 knots at 20,000 feet. So if you've got up to 20,000 feet and think, oh, or higher, and think, oh, good, I've got my diamond height now, I'm going to speed down before it gets dark. It's very easy to exceed VNE because your ASI is lying to you. And if you exceed VNE, you have that potential for loss of control or flutter and something breaking off. And so your descent might be actually a little bit more rapid than you had intended. Right, moving on again. The next part of the flight envelope is defined by JAR 22 or CS 22, and it is the limits of 4G, 5.3G at the stall line for category U. These limits are where you could exceed the load limits of your aircraft. So 4G at the design speed, BD, 5.3G at the stall line. So I'll just draw those in. There's 5.3 and 4, and there's a line joining those 2 points. And this is known as the load limit. If you exceed that load limit, you are likely to cause what is known as elastic damage. It might not cause the component to break immediately, but it will probably deform that component. And if you do that multiple times, it is then likely to break. Obviously, there are positive and negative equivalents, as I've just said. We've got 4G, 5.3G, and -1.5, -2.6. For the aerobatic category, the limits are +7 up here and -5 down here. But for the utility category, which is most gliders, most non-aerobatic gliders, it's +5.3 and 4, -2.65 and -1.5. So those are limits which are just defined. They are defined by CS 22. Exceeding these limits may cause damage. I've already mentioned that. There is a safety factor built in, which is the ultimate load point, which is 1.5 times those values. So if you exceed the load limit, you cause elastic damage, as I just mentioned. If you exceed the ultimate load, something will probably break. Something that I kind of skipped over momentarily there is you take that 5.3 line intercepting the stall line, bring that down, you get VA, which is the maximum maneuvering speed, which is marked on the placard and the ASI, and that is the speed beyond which you may not use any one control. You can use below that speed, you can use any one control up to maximum deflection, but not above that speed, and that is any one control. It makes no mention of 2 controls or 3 controls. So I'll move on a bit because time is pressing. If you go to CS22, you will find exactly the same diagram illustrated, and they talk about these points N1, N2, N3, and N4. N1 5.37, N2 4, 7, N3 minus 5, minus 1.5, minus 5, N4 minus 2.6, minus 5. So this is just defined in CS 22.337. So if you deflect 2 or more controls, then the shape of this envelope changes, and you may well then be outside the flight envelope. So this VA is for one control only. I don't know if you can see that. On my screen, I can see a canopy here, but you may not be able to see that. So why is this true? Why is VA defined for only one control? If you imagine this aircraft flying towards you and consider what the lift distribution is across the wing, it'll be something like that. So there'll be quite a lot of lift generated here, quite a lot of lift generated here. Towards the wingtip, there's very little lift generated. Right up against the fuselage, there's very little lift generated. So the lift distribution is something like that. Might not be exact, but we're approximating here. So if you add all the components of lift here and all the components of lift here, you can get a lift force here and a lift force here, which is the summation of all those little individual components. Now, both of those forces act through the center of pressure. The center of pressure will be somewhere in the middle of the fuselage like that. This is flying nice and straight in a straight line. Now, what happens if we deflect the ailerons? If we deflect the one to our left upwards and the one to our right downwards, this is an exaggeration, but we generate more lift on this wing. We generate lift here, which we didn't before, and we generate no lift there. So the lift profile changes dramatically, and the amount of lift generated by this wing and the amount of this lift generated by this wing changes dramatically. Again, I'm exaggerating for effect. But the point is that the center of pressure has moved out onto this wing somewhere, and the flight envelope is a completely different shape because a lot of lift is being generated by this wing and not very much lift is being generated by this wing. Things have changed dramatically because we've deflected the ailerons. I'm skipping forward simply because time is passing. This is a gust envelope which is plotted on the same coordinate axes. Again, CS22 defines what these gusts are. 15 and 7.5 meters per second, which is approximately 30 and 15 knots. So since everything else I've done is in knots, I'm using 30 knots and 15 knots. And what this is saying is that the normal load factor on the glider is 1. And if you hit a gust, either positive or negative, then at 60 knots, you will generate an extra load factor of approximately 1, or down negative, the down gust approximately -1. If you hit a 15 knot gust at 120, you'll generate an extra 2.5 positive or an extra 2.5 negative. So here we are with a, yes, that's just it, saying what I've already said. So if we now superimpose the flight envelope on those gust lines, it looks like this. So again, it starts to look much more complicated, but the gust lines simply show us how much extra stress is added by flying into a gust. So CS22 says that a 15 knot gust needs to be considered at the VD speed, the maximum design speed. So it has to allow for a 15 knot gust at VD. For the 30 knot gust, so you must, the glider must be designed to be capable of withstanding a 30 knot gust acting normal to its flight path up to the stall line. So the VB speed is what we know as rough air speed, and it must be greater than or equal to VA. We've already marked VA on here as the point at which the glider will stall with 5.3 G, or load limit of 5.3. In this particular case, the 30 knot stall line has cut that corner off. So VB will actually be a higher speed and will be round about 100 knots. Quite often, due to the shape of the curve, this 30 knot line will not cut that corner off, in which case VB will be the same as VA. So the rough air speed can be above the max maneuver speed, but quite often they're the same. Going back to our PERCOS, it displays symbols which we've already associated with the flight envelope. VA, max maneuver speed, is displayed at 90 for category U or 105 for A, and VNE is 132 or 145. So we're all familiar with these figures. We just haven't previously not necessarily understood where they came from. You may not be able to see all the detail in the next slide. This is just captured from the PERCOS flight manual and explains what the various segments of the ASI indication are: green arc, yellow arc, red radial line, and yellow triangle. I won't go through all of those in detail. Also from the PERCOS flight manual, the airspeed limitations: VNE is 132, as we've just seen marked on the ASI, VA 90, 105, and the rough airspeed they give exactly the same as VA. So VB, called it VB on the previous graph, although PERCOS, the PERCOS flight manual calls it VRA. VB in this case is the same as VA. So it says, do not exceed this speed except in smooth air, and then only with caution. And VA says, do not make full or abrupt control movement above this speed, because under certain conditions, the sailplane may be overstressed by full control movement. So if you're doing aerobatics as taught by the BGA, which is quite positive control movements, and you're above VA, you may be contravening this statement here. Do not make full or abrupt control movements above this speed. Again, from the flight manual, just to reinforce what I said before, allowable positive load factor +7 plus -5 for the aerobatic category, for the utility category 5.34, 2.86 -1.5, all the same numbers that we've seen before, just restated in the boat course manual. So just a reminder of the earlier flight envelope showing the gust lines. Let's just now imagine that we are going to do, let's get rid of all that text. Let's do a very gentle loop. So you might think that if you were flying at 110 knots and pulled only 3G, there couldn't be any possible problems. But what if there's a 15-knot gust? Okay, 15 knots is significant. I will accept that. On a nice thermic day, you might get 10 knots of lift, which could be close to 15-knot gusts. But anyway, let's assume that it is a thermic day and where we decide to do a gentle loop in our notional aircraft at 110 knots. 110 knots is about here on this graph. So we draw in a load factor of 1. So before we start, we're experiencing 1G. We haven't done anything yet. We're in straight flight. If we hit a 15-knot gust, okay, that's the exception, but we might hit a gust of less than that. But a 15-knot gust will add 2 and a bit load factor. So we'll add that line there, and we've hit a weak gust. Now we decide to go into we're in the middle of our loop, and we're pulling another 3G. That puts us well above that load limit. And so we're into the elastic damage of our aircraft. And it's well into that elastic damage. So this gust didn't have to be 15 knots. It could have been probably 7 knots and still got us above the load limit, which is like the lift of, I don't know, 7-knot gust, lift of say 5 or 6 knots. So it's not a good idea to be doing aerobatics when there's lots of lift and sink about. We've exceeded our load limit by a significant margin there. Oops, sorry, press the button. Right, moving on, let's consider a glider on a winch launch. This is stolen from Mike Fox, this illustration. These are round figures. They're not precisely calculated. But let's say that the weight of this aircraft is 500 kilograms. There's a 1200 kilogram pull on the cable through a black link. And the pilot is pulling furiously back on the stick to keep the nose up. So there's a 300 kilogram load on the tail, downwards. 300 plus 500 plus 1200 is about 2000. So this wing is generating about 2,000 kilograms of lift during that winch launch. 2,000 is approximately 4 times its weight. So that aircraft has a load factor of 4 going up a winch launch. Load factor of 4, just to underline, is there on this graph. So if you now encounter a gust whilst you're on a winch launch, then you will increase your load factor, in this case by about that much. And again, that puts us above the load limit. Now, it's also above the stall line. So you might say, well, that's all right. We will stall. Wings will stall before any damage is done. But actually, it's below the 25% temporary line. If you remember right back at the beginning, I said that for a few seconds, the wing can actually generate 25% more lift until in a transient state until the wing actually stalls. So for a few seconds, that extra load is there, and you may be exceeding the load limit. Most people will have seen these videos. This is courtesy of DG, and they are testing a wing to destruction. Now, Mike Fox likes to show these videos and say, if you get disorientated in cloud, don't open the air brakes, pull on the stick. The reason why he says pulling on the stick is the safest option is because they test the wings like this. Again, it's a shame we haven't got the sound coming out. I don't know why the sound isn't coming out. It did when we tested it. I'll say it again, this is why it's better to pull back on the stick than open the air brakes. Because most wings are designed to take an awful lot of load. Obviously, I didn't start the two videos at the right to synchronize, but you get the impression. If we had time, I could go through this one, which is exactly the same structural wing test for the JS1 Revelation. This is actually quite good because it shows you the view of the loads up here, and for some reason my laser pointer is not showing on your screen, but there are 3 views. There's a side view, a front view, and in the top right hand corner it's showing the loads. But I won't go all the way through that because it's essentially the same thing but by a different company. So moving on. Conclusions. This all looks horribly complicated, but if you break it down into its individual bits and pieces, it isn't. That curved line on the left is called the stall line, and to the left of the stall line, flight is not possible. to the right of the stall line, flight is possible. Here we've got VNE. Flight to the right of VNE is stupid, and you're likely to break something. Up here, we've got a load limit line, which is defined by CS22. And the designers of your aircraft have designed it that it in such a way that it should reach those limits without problem. But again, if you exceed those limits, you are outside the design envelope. So the design envelope is the blue bit in the middle, the flight envelope. That's the conclusion of the talk. So if anybody has any questions.